Hi, everyone. Thanks for joining us today. I'm just gonna, till other folks are joining us, I'm just gonna start with our introduction slides, telling a bit about ourselves, who we are, and what's this program. So Integrated Design Lab is the research branch of University of Idaho College of Art and Architecture. So we are an educational group focused on energy use of building. And these lecture series are sponsored by Idaho Power Company. I don't see anyone new, so I'm sure you all know about this, but for the folks online, maybe if you're Idaho Power customer and if you're working on a new construction, retrofit, or energy model and could use a hand, you're here to help. Up to $4,000 of worth of our time and team is going to be covered by Idaho Power. So it's going to be free for you. Beyond that, there's going to be a fee. So feel free, please, to reach out to us for more information. There's a form on our website. You can email us directly or reach out through Idaho Power. We also have some tools available for checkout through our energy resource library. So if you are doing an energy audit or HVAC performance testing, we have new tools like the data loggers, and no need to plug it into your system. And if you are not sure what kind of equipment you're gonna need, we are here to help, and we also can provide a brief training how to use them. Then we have these BSEC lecture series. Our next one is going to be on June 18th on performance-based code appliance, appendix G. Idaho Power has also a separate program for commercial and industrial energy efficiency program. It provides incentives for projects like retrofits, new construction, and major renovations. That can include things like expanding a building, adding a new load, or say like installing AC in a previously unconditioned space. And for larger design support, Idaho Power also offers a professional assistant incentive that's different from the technical assistant that I mentioned earlier. This one is up to 20% of your project cost and with a cap of $5,000. So today, we are very excited to have Dr. Robert Lauer. Did I pronounce it correctly, Robert?
Yes.
So our speaker today is the lead data scientist at Tagup company. Robert has a background in high energy physics research and now leads the development of AI models to optimize HVAC systems in real time. I'll let you, if you want to add more information, share with us. So I'll just hand it over to you, Robert. And thank you so much for being here.
Thank you, Fanas, and thanks everyone for joining us. I'm Robert Lauer here at Tagup, so I'm located in Boston here. I'll say a few more words about our company in a moment. Online, so my colleague Avery joined us, who helped with making the connection to your group. And I'm very excited to talk to an audience of whom I know very little, but what I just learned and prior to the talk about your group, I think there's just a large overlap in things we are trying to do, and so it should be an interesting discussion. I'll talk about AI-driven HVAC optimization, and essentially in one sentence, this is for us using our product called Manifest, which combines machine learning with physics to optimize the HVAC equipment in real time, which means in particular in response to changes in weather load. And the next 30, 40 minutes or so, I'll talk about all of these aspects, what that means, how it comes together in a product, and how we are delivering what we're talking about here. Let me just introduce our company, Tagup. So we are originally based here in Boston. We have now people in different places across the country, in particular a major office in New York City, and then a few people on the West Coast too. We started based on the founders, both come from MIT, and started a business to deploy software applications that use machine learning to optimize decision making in the industrial space. And that can, of course, mean a lot of things. And we have worked over a few years that I've been with the company also on different fields, including power generation and transmission equipment, and then more recently, logistics optimization, often in terms of government contracts. And on top of this, we have a large experience in dealing in the private sector industry with buildings and what we can optimize inside these buildings, so in particular the cooling systems. And that's what I'll be talking about. This slide is probably, you know more about the details here than I. It's just like a motivator. Why are we talking about building cooling if there are so many things we optimize? Well, it's such a major part of the electricity budget in the commercial space. And the top 8 consumers is space cooling. And of course, things we do can also have an effect on refrigeration, which is listed here too. These data from 2022, they summarize this as about 153 billion kilowatt hours in electricity for space cooling alone, which amounts to 66 megatons of CO2 released. So both from a commercial view and from ecological view, there's of course a high desire to reduce the amount of electricity and other resources spent. And our approach to this is, let's say we have to take the load as a given. We have a fixed cooling demand on the building. We need to remove this. There's nothing else we can change about that. How do we do this most efficiently with the equipment that's already in place? So we are not a company that installs new hardware besides kind of the gateway connection, and I'll come back to that later. How do we communicate with a building? But the cooling equipment is already in place. And then our approach here is that we use and integrate the observational data from the sensors at the site with very carefully distilled domain knowledge, so that we can enable our customers, the operators of these buildings, to make better decisions and do that without the need for like years or even months of historical data on which we first need to calibrate everything, but rather put it in place and very quickly optimize the system. And the big advantage of using AI here is then that we can react faster and incorporate vastly more data than humans traditionally could, so that we achieve what we think of near or potentially superhuman performance for making these decisions. And of course, in the traditional setup, these decisions are informed by intuition, by the hard-won experience and the codified rules that might already come from the manufacturer. And of course, that is in general suboptimal. I mean, intuition can turn out to be wrong, and experience can overemphasize past behavior and make someone less susceptible to new options. And codified rules are good, like on average, but can, of course, leave out a lot of edge cases for which the optimization can be particularly important. We do all of this by dramatically reducing the amount of time and effort it would take to experiment in real time with these parameters that we have access to. And that's exactly where the AI comes in, and our software can do this experimentation in a very safe and cost-efficient way. So the problem specifically on the cooling side that we focus on is kind of in a very simplified way captured here. So let's say we start on the right side at where an air handling unit comes into play. So somehow the air through all kinds of VFDs and equipment, the heated air has made its way into the air handling unit, and the heat gets dumped into a chilled water loop. There's some kind of chiller, and of course, in general, this will be more than one and can be different types of chillers that removes that heat and moves it into a different circuit. So generally, I'll talk about a setup where we have a separate condensed water loop, which then has to get rid of the heat through, in general, a cooling tower. So already in this setup, even if we deal with a very small building, which only has like one of each of these components, we have at least 3 separate loops of fluids that all run at different temperatures. And then most importantly, on the right-hand side, we have potentially quickly varying load on the building. And on the left-hand side, we have the outside weather conditions, which also affect how things change. So a lot of parameters and a lot of potential to optimize how these pieces of equipment run. And of course, I even only allude here to other pieces like the individual pumps or the valves that are on the system that play a role too, and that affect the feedbacks inside the system. So for most of the talk, let's just assume the only control I have access to is the set point of the condenser loop temperature. So in the middle left of the slide, the temperature at which the water circulates, which is controlled by how fast the fans and the cooling towers run, but of course has major effects how efficiently the chiller and any downstream equipment will operate too. This problem alone, is quite complex. I mean, we have nonlinear dynamics of these at least 3 different fluids that I already mentioned, plus the air outside. Things can vary quickly, and basically an automated optimization needs to be prepared to quickly react to these changes that might not be known beforehand. On top of this is the cost that it takes to operate this, which is not like a single factor. Yes, there's an electricity rate that changes somewhat slower, but it will change from month to month with most contracts, plus demand charges and so on. But we also have water that evaporates, so water needs to be refilled. So there are costs for the water itself, for the chemical costs. We have different chiller systems that use steam instead of electricity and so on. So all of these things have to be taken under consideration if we want to holistically lower the total cost of operating the system and not just one single component. To do this traditionally, system operators and companies that optimize this need very long time scales over which to run measurement and verification, precisely because of all these factors and of the specific ways in which a building is or the system in a building is put together. So rule-based systems like those proposed by Azure standards and so on, they generally aim for finding very good and sometimes extremely detailed solutions to do this. But in our experience, it is rare to find a building where all like the latest recommendations on these rule-based codices have been actually implemented and are running. There's sometimes often actually some uncertainty what exact settings are used and so on. So this leaves like a vast amount of space to be optimized. And on the other hand, the operators that control the equipment typically have better things to do than to sit in front of the machine for a large majority of the time and just apply these changes manually whenever they think or someone tells them to do this. So we are really aiming here for an automated way to do this. So that is the problem, and the way we approach this is AI or machine learning in a very specific way. We want to build a model that can take in all of this data, sensor data, which probably comes on every 5 or every 10 minutes or even more frequently. We have the data on tariffs and cost rates that have come from a different source. And then, of course, the equipment data itself, excuse me, like what is the specific capacity of each piece of equipment and so on. And the way we've approached this over the last 2 years, where we have deployed this technology across like a large variety of buildings in this country, is building a model that takes in the data and then builds this holistic simulation of the total consumption across the cooling system while it operates. And we have found that if we have 4 to 6 weeks of operating data, we can train a model to give us a very precise forecast what the system will consume under any given outside conditions, on the weather on one hand, load on the other side, and then under any settings of the control signals we have access to, which again in the basic case that I'm describing here is actually just the set point of the condenser loop, the temperature at which this water circulates. So we achieve percent level accuracy for the forecast of the whole cost or the individual components, which are typically electricity, water, and steam. And in this kind of simple formulation, we can simply very quickly scan what are the options and what is the optimal setting at the point in time that we are making this calculation. And then, of course, we can recommend that setting to be implemented. The pictures here are not in fact the real data from cooling system. This is basically just some illustration. It just highlights the fact that we're using a Gaussian process approach under the hood for this type of model, which is one of potentially different machine learning approaches you can use. It is one that has the big advantage of automatically giving us an uncertainty, which is important in determining the accuracy and then also communicating the results to the end user. So we don't only predict or tell people what is this one setting they need to change. We'll tell them what exactly is the difference in the electricity, water, and steam consumption with this, and what is the uncertainty on that prediction. Now, this is kind of the first phase of modeling that we have rolled out over the last 2 years. And then over the last half year or so, we have been busy upgrading this to a much more refined system. But actually, before I come to that, let me give one example of what that means in practice. So this is actually some actual data from a smaller system. So if you just have a loop where you consume water through the evaporation in the cooling towers and electricity for running the fans, and then most importantly for running a compressor and a chiller, plus the pumps that pump the water between these, then what we can model is under any of the given set point choices that are here, maybe the x-axis, And for the different times of day for which we have data, these take on very different shapes. So if you were just looking at the lower picture and just wanted to optimize the electricity, you just have to find for every of these hours that are represented here, the minimum setting. What is the set point where you use the least electricity for all the equipment together? But of course, if you also want to factor in water consumption, then you actually have to consider both of these pictures at the same time and optimize in this way. And as you can see, even for like single day or part of a single day that's represented here, the shapes of these curves can vary, which has a lot to do with the weather and the load that changes. And then on the right is just an example for what that would result in. This is somewhat simplified, but if you just look at the orange line, which represents the set point, that's actually recommended to the system, and in purple, the wet bulb temperature of the outside air, then you can see that this will actually result in a mix of things. On the right hand, this is more like a rule-based. It's nearly like a fixed approach type of signal where you vary, like you raise and lower the set point based on what the wet bulb temperature does. But on the left is very much not so. And that has a lot to do with factors like the load that the system learns about, at what point we actually have to switch away from a very simple like strategy that looks like rule-based and go to something that truly optimizes the system under the given conditions. I know that, as I understand, this kind of was a question also in terms of how much do we understand how much better AI is than full implementation of rule-based system, like ignoring the fact that it's non-trivial at all to implement these rule-based systems too. So I can't give you like a general number. This has a lot to do with how different buildings actually operate. I have like one of the examples we see, okay, if you just implement at a medium-sized building a fixed approach strategy, what kind of set points do we see over the course of a few months? That's the on the top. And then what are the set points that our system recommends for like the same time? And I show this because you see it's already a different shape. So at a very high level, you see that the system will do something that's significantly differently from just shifting a rule-based approach. We have found, as a general rule of thumb, that you unlock something like 50% of extra savings, but honestly, this number will vary a lot based on the size of the system and the scaling of the equipment and so on. So let's continue to the enhancements that we're busy rolling out now. So what I've described is kind of before is a simple AI system in the sense that it is one machine learning model that takes all the input and outputs the different predictions for electricity, water as a whole. Now we're switching to a truly physics-based model where each significant piece of equipment in the system is represented by its own model. And this model internally knows about the basic physics of that piece of equipment. So it encodes like the basic rules about how a chiller transfers heat or how evaporation occurs in a cooling tower under different fan speeds. So we now have a digital representation, not just of the system as a whole that we want to optimize, but of each piece that makes up the system. And second, the parameters that the AI process then learns have a direct real-world interpretation. We can look up like the efficiency curves of each of these pieces of equipment and understand exactly what the changes we implement will do in terms of the efficiency of these pieces of equipment. The individual measurements that are needed for that are represented via probabilistic distributions, which also means that if there's uncertainty, like a sensor is miscalibrated, a sensor suddenly turns off because it's broken, or was never installed at the place where we want it, we can still represent each of these inputs to the individual equipment models with a distribution, and that distribution will have a higher uncertainty if that sensor is not operating well or even missing after some time. So that is also a crucial difference to the requirement by like a simple model that needs the inputs from all the features we exposed it at all the time. So that is kind of step one of the new phase of modeling, and step two is then what we call generative reinforcement learning, which takes this physics-based model of each piece of equipment and truly runs a Markov chain simulation of changes in each of these input parameters, given what happens outside in the world, so the exogenous data from load or weather that changes, and the changes that we have control over, the different control points that we want to modify. So we are not only simulating the state of the system at any given point in time for which we have like the input data, but rather from that point forward, we can just let the simulation run on like typically a 5-minute interval basis and trace the changes in all these temperatures of water and gas throughout the system. And at any point in time, we can still use the observed data to keep this simulation grounded by using the probabilistic distributions that I just mentioned and aligning the parameters that describe them based on the latest updates from the observables. So what we are really enabling with that is complex multi-parameter optimization. So now we can really go away from changing one setting at a time and having, because we can generate how the effects to change more than one of these pieces. This is why we call it generative. And reinforcement learning is then, instead of now having to scan all the possible options and choosing the minimum, we can use much smarter techniques like reinforcement learning to scan the parameter space faster and more efficiently and find the optimum at each time. So this is the phase 2 stage of our modeling that we are now rolling out in our production setting. And on the next few slides, I want to go into a little bit more detail what that means, rolling it out at a production level. Because, I mean, the machine learning is the core piece for this and for all the other applications that we serve at our company. But implementing it in a way that we really achieve results quickly and transparently to the customer is the second like, major piece in this game. So what I just described is how do we simulate the different control strategies via this machine learning engine that allows us to get results for changing a control set point and understanding immediately what are the effects on the consumables and when do these changes have to happen. Now, to show how this really works, is we need the M&V piece. We don't want to turn this on for 1 month and then spend the next month going back to what the system has done before and then compare the two. I mean, that's kind of the traditional approach, but it of course wastes a lot of potential time that we could have optimized the system. So instead, we are using the insights from our model and the accuracy metrics we have to determine how precise the model is at any given time to bring the model to a point where it accurately shows any remaining uncertainty and the difference between the different scenarios, and then visualize that in our platform as a full insight into how this affects the calculation for the customer. we can do this because we can very quickly rerun these scenarios that every time anything changes. And on top of that, we are retraining these models very regularly, at least every week. Basically, we have new data coming in, and the whole model training is repeated to make sure that the latest data doesn't change some important considerations. This over time, this particular that equipment, of course, changes with time and how it reacts. It also is important to see how changing load patterns, for example, affect this if a building starts to have different usage, for example, at universities or so, that can be an important consideration in summer versus winter. And none of these things are hard-coded anywhere or set via manual setting. Right? We do measure load implicitly, and therefore any changes will directly be translated into how we decide, or rather how the system decides what to optimize. So that's what we call constant retro commissioning, to take the latest data into account. And we receive the data for most systems on a 15-minute basis, and then at least every hour we run that processing and recommend new control decisions. So that's kind of visualized here. We get this latest data. Automatically we are creating new recommendations, and in all cases that we have deployed this in the HVAC space, these decisions are actually implemented automatically. They can be overridden by the operator for whatever reason they choose, but if not, then day or night this will be implemented directly. And then of course, and on these timescales of an hour, weather and load actually can change in the building, and we'll use the new data to revise any recommendation constantly. Okay, that's just an example how that would look in a BMS. So in most cases where this has been implemented, the BMS screen will then have an additional value for our recommendations for all the control set points that it affects. And the crucial piece here is also that we deploy the solution on top of the existing BMS. I'll come back to that in a moment, but it doesn't require a whole new rollout of any of the user interfaces that are used already. And as a second piece, we then have our web application that customers have access to, that highlights not only these control changes, but also the effects on the consumption side and how the cost savings are generated. So we have already deployed the system across, I think it's actually now more than 40 chillers, in different states. On average, the savings we're producing are 10 to 20% of the system operation costs. And of course, depending on the building size and location, it can be different times of year where more or less of these savings are generated, which is another important piece of the AI solution, to really realize the optimization in the right moment and not find the average best solution for the whole year. We focus generally on larger plants and buildings, simply because the return of investment of the initial installation makes more sense at these scales. And all of this, all of the calculation, happens on our cloud software, which is fully compliant with various security standards in terms of full encryption and communication between our platform and the gateway at the site where we optimize. I think I won't go through all the details here, but basically there are several stages. Once this is newly deployed at a building, the initial survey can be very quick. Basically, we ask for a standard list of nameplate data and current sequence of operation on the system to do a basic qualification of the site and a very rough estimate of the potential savings. And then if that is at all promising, then we can quickly move to integration, which typically includes installation of a small gateway device, basically just a small industrial computer that we set up at the site that has access to the subnet of the BMS or BAS that gives us access to the sensor data that's already collected and to the control set point. And then on the other side, the gateway communicates that data back and forth to our cloud. In most cases so far, we haven't installed new sensors at the site because for the basic condenser water set point optimization, nearly always all the sensors are already there. Basically, we need access to the power meters of the major pieces of equipment and then to the temperature sensors for on the chilled and the condenser water loop side, and if possible, a flow rate sensor. And that's about it for the basic solution. Of course, the more sensor points there are, the more quickly we can reach a precise model. But the initial threshold is quite low and therefore generally doesn't require any hardware updates and therefore also not any downtime on the system while installing this. Then comes what we call the observation period, which is not actually just a passive period. This is what traditionally was 1 to 2 months because of the 4 to 6 weeks I mentioned earlier. It takes to get to an accurate modeling, but we have switched to a mode where even during this time, we already start a simple rule-based optimization of the system. In particular, if as many systems do, they just have like a fixed condenser set point, so that we can already start creating savings in this early phase while gathering the necessary data to make the model more precise. And then once that's over, we're in the full optimization phase, where automatically every hour the system gets an update. And on our side, we are still basically treating this like the learning phase before. We'll still automatically retrain the model regularly and release the new and updated model in a semi-automated way with some supervision and around monitoring if something changes in the system that we might be aware of or that we want to inform the customer about. So, I mean, we have different case studies. I just put this in here because it was one of the earliest buildings where we deployed, and it was one of the ones that was in its typical range. I mean, here it was 70% of the first half year that this was deployed. Actually, in our portfolio now, this was a rather small building, and we are currently working more heavily on bigger size buildings like district cooling plants, for example. The web application I mentioned earlier is important, not only to show the results of the optimization, but also to do the setup. So we are moving to a mode where we use partner organization, and one of our biggest partners is Baltimore Air Coil, that produce cooling towers. So they have the contacts to the buildings, and as soon as the basic qualification phase is over, we can open our platform for people from our partners to set up the final integration. So once the communication with the BMS at the site is established and our cloud has access to the data that comes from there, a operator or integrator can use our platform to make sure that these sensor points are mapped to the right counterparts in our system. So we have a full data model of what points are needed and are possible to map to for each of the pieces of equipment at the site. And then the partner can just make sure that this maps to the right points, given the kind of expert knowledge that's often required to know about the scheme that they are labeled and so on. And on top of them, they have always full access to set the safety margins. So one of them is shown here on the upper right for which changes we can implement in general, what is the baseline this is being compared to, and gets a full insight into how this is configured into our site. At a higher level, if we get to the operator or then facility manager, they will mostly want to look at the summary of what the optimization and results to, and that's a screen that looks like this, where we show how the savings grow over time, and we can split this up. I mean, here it's shown for the total cost and then the electricity consumption. So once you have also a steam chiller, say, on site, this would have an extra tab for steam and so on. So you can drill down into the individual components that make up the savings. The other core piece then of the platform is the one I talked already about earlier a little bit, how we visualize what we do under the hood for M&V and what the customer wants, of course, in the end to see, like how do we calculate these savings. There are basically 4 pieces related to that. One is establishing the baseline, so understanding from interviews with the operators or their documentation what their operations are without the extra optimization step. And then what we do as ongoing calculations, and what in the IPM MVP jargon is called type D, is that we simulate the operation cost under the different scenarios. The baseline that would have been in place had we not installed our system, the optimized way that our system will control the system, and then what actually happens, because as I said, it is possible for an operator to overrule what is being recommended, or maybe there's some other issue that temporarily the system is disabled. So all these scenarios will be calculated at any given time in terms of the impact on the consumption. And then this example here on the right, the platform will then visualize the uncertainty on these predictions and the comparison of the different scenarios. On top of that, we do some randomized control trials, meaning to make sure that the machine learning model gets exposed to what would have happened in a baseline scenario on a regular basis to recalibrate any remaining uncertainties. This is a setting that we normally revisit with the operator in regular intervals, and it stays far below anything like 50% time. It's typically more of at most 10% of the time, so at most like 2 or 3 days out of a month, where for a certain time period at a random interval we would switch back to the baseline mode this. And all of this together gives us an ongoing value estimation that includes all the latest data into these verification calculations. That's that's just a bigger version actually of one of the examples I just showed in the previous version. So we're both in the terms of summaries, we can compare the cost or the CO2 emissions or the electricity for the implemented scenario. So what is actually happening, and then compare it to the baseline in the graph that is the purple line, and the actual line, just to make sure that the model is well calibrated, and the actual line, as you see here, actually is within the uncertainty bounds and is represented by the model calculations. And in the app, this screen can then be chosen for any arbitrary time period people want to inspect. Yeah, this brings me already to my last slide, and of course, then I'm happy to go into the discussion for any questions. So, in summary, we achieve real-time optimization of a cooling system via AI models that precisely forecast the consumption of each of the resources that are needed, and we lower the costs holistically on the whole system, considering all the feedback happening between these components. We're now switching to a new physics-based and fully time-evolving model setup, which unlocks even more details about the individual pieces of equipment and about the accurate forecasting into the future beyond like the current time optimization that we are already doing. And then all of this is packaged in a program, in a product that simply integrates with all the existing systems and sensors by basically adding an extra layer of communication on top of the BMS to interact with our cloud where these calculations happen and return the results in real time via our web application. Yeah, thanks so much for following this and joining me here. And I'm very happy to go into the discussion now.
I'm just checking if you have any questions in the chat. Okay, I'll go with the first question. You had a slide, there's a black histogram showing that how static sensors savings compared to AI optimized savings. Can you show that again? And I saw that they had different patterns. Could you just explain a bit?
Sure. So I like specifically to go into this point because I know that's like a general question. What I showed here is just an example of distribution of the set points, of the optimized set points recommended by a rule-based system on the top and our AI system at the bottom. So this does not expose the exact savings, as I mentioned verbally. In this case, for this period, basically the savings unlocked roughly an additional 50%, but that's not yet a rule of thumb because how effective either of these strategies is so much impacted by the specific conditions at the site. So what I wanted to highlight here is more that after, like you could naively expect that after our AI model learns everything, it will basically reproduce a fixed approach or similar rule-based system. And that's not the case at all. And this is just one visual way of showing that the shape of the histogram in this case, like one of the ways to summarize what happens over a given number of months is quite different. But it's hard to show the exact differences without scrolling through lots and lots of time series of the actual set points because they change every hour and the web bug changes every hour and so on.
Okay, thank you. Got it.
Sure.
Can you hear right now or not?
Yes, I can hear.
So you are only validating your model up against the individual building itself by turning off your controls, correct?
So that is, yeah, so we are using for the actual training the data only from the building itself, but the physics-based setup of the model, of course, incorporates what I call expert knowledge, but like general knowledge about the equipment and so on. And then the validation that happens is not a traditional on-off type validation. That's part of it, but the actual validation is the type D validation where we bring the simulation to an accuracy level that even while we're not running the baseline scenario, we have a precise prediction of what the baseline would have consumed in terms of electricity and water and so on, and then compare, and then basically calibrate that prediction on a randomized basis by switching back to the baseline. Yeah.
Okay. Where I don't quite understand how you were getting then your uncertainty quantification at 5%. You mentioned that right off the top of the.
This is, yeah, no, it's a good question. It's one of many metrics. So there's basically there are ASHRAE guidelines about like uncertainty levels on to implement control strategies. That's where you can compare the 5% to like a rule of thumb of 10%, but that's just on the relative error. Like the actual metrics we look at are others like CPRS metrics that includes the width of the uncertainty bands and a few other metrics generally used for machine learning models. So the 5% doesn't really, that's just one average error metric, but that we calculate per implemented set point. So if I switch to different scenarios and different set points, then I need to know the uncertainty of each of these. And that is kind of a threshold where we want to push all of these under 5% before we consider implementing that, but it doesn't quantify the uncertain, the whole model. That's only like one of the metrics.
Yeah, I get that. So what were your models achieving in terms of validation? Like what were you down at percentage wise?
Yeah, I mean the 10% is the threshold for the initial observation. 5% is if it runs for several months or so, the average, and then from then on it kind of slowly decreases typically. But then, so I don't have a graph here for it being split up into the set points. So the overall error is not really relevant because it averages over so many different weather and load conditions and across time. So these are different plots that we make that split it up by time or by a set point and so on. And so 5% is the number that has more to do with average overall time and load conditions, but split up by set point. And depending on how you cut it, you get kind of different numbers. So I don't have like one number for everything together.
Okay.
Is there further opportunity to optimize the performance of chilled water systems by also controlling like air handling unit supplier temperature and chilled water set point?
Yeah, thanks. Great questions. Absolutely. So I didn't include this here because would have taken a little bit too much time. Basically, we're currently piloting adding the chilled water reset to this. And the reason why this is not done from the get-go is because the closer we get to the air handling unit in there, the more we expose the system to potentially affect tenant comfort, right? I mean, here we have like very strict constraints. So we have a load, we definitely need to remove that load from the chilled water circuit, and we change the condenser set point, and there will be no effects on the chilled water side. Like we monitor that, and there are safeguards in place to not ever affect the system's ability to cool basically the AHU and everything downward. So the closer we go to the other side, the more data we need to monitor what's actually happening in the building. So then we do need to look at like the thermostats in the room rather than just the chilled water temperature to see that we're not changing anything in unwanted ways. And that requires typically a higher threshold of implementation to have access to these sensors and to monitor them at the same time. So we do see the potential with chilled water reset to, on top of the savings I've shown, to add another 10 to 20% for a standard like central chiller plant system, just because they basically, I mean, they're to some sense orthogonal in how they work. But to do this, we still need to build this in integrated model to make sure, that we are not counteract these changes on the condenser side, or rather that we are in danger to how this heat is removed. So that, and on the other hand, actual staging of the equipment, in particular chiller staging, if you have a multi-chiller system, those are the two pieces that we're currently looking actively into pilot sites to prove out how much more savings that can add to the system. And our new equipment-based modeling approach is very much enabling that, to have these insights at the individual equipment piece of these additional set point changes.
I have two questions. The first question I have is when you go in and let's say the AI system decides that it wants to change a set point, is it dynamic and does it change over time? So let's say it wants the set point to be X and then it changes to X prime. Does it evolve over time?
Yeah, we consider more like safeguards in place, but basically we have limitations that our operators can have input on, like how quickly are we allowed to change the set point. Like effectively, like one of the limitations that we typically change it at most once per hour. That's like default setting, and it's very rare to have a system that's for which it would be advantageous to do it faster than that because of their feedback times and so on. And on top of that we also have like a limitation of how much the set point can change in that 1 hour. Effectively, though, it's really more what we've seen. It's mostly the feedback times in the system that determine that, and not so much what the control logic says, because in the end, fans need to ramp up, water temperatures need to mix and change. But there are several levels of settings that we discuss with each system operator to get the input on.
Okay, thanks. I think that answers my other question. Thank you.
Okay. Yeah, thanks.
Robert, can you go forward a couple slides so that you have that slide with the same graphic, but it's sort of blown up a little bit?
Yeah.
So I'm just wanting to make sure that I'm reading this correctly. So for that graphic, the baseline is what you would predict their usage would be if you weren't using your AI-driven model. Right. And then the actual is what they're using. But then you have that little red plus or minus in a few different places. So is that just your model uncertainty?
Yeah, that's a 95% confidence uncertainty band, so really wide uncertainty band. And so that basically tells us the overall uncertainty. What it hides a bit, and that's, we haven't visualized that yet, is what it means for the savings uncertainty, because part of that uncertainty is the overall uncertainty, for example, in like the calibration of the humidity sensor and the wet bulb. So that if that is the uncertainty that would affect both the baseline and the implemented setting that's shown here. So, but yeah, this is the uncertainty. As you can see, it actually gets like a little bit wider at the right side. That's because it was probably at the end of or past any period that data had been trained on. I have to look up which system that was. But in the early optimization phase, these bands do change relatively quickly from week to week. This is why we still have, like, this is all set up, a period of over a month where we calibrate them to make sure that they shrink down to a level you see on the left side.
Thank you.
Sure.
I guess that was all of the questions. Thank you very much for your time, Robert. It's a pleasure, and
Yeah, thank you all, and thanks for the discussion.